Hi guys, making a video for question 45 in Tsokos. This is the Cambridge IB Physics IB textbook. So yeah, just going to kind of talk through it. Associated with this, there was a question regarding acceleration and displacement and the angular speed and frequency. I think that probably stemmed from the equation in the question here. The y equals 5.0 cosine of 45 pi t. And I think someone was asking about, well, how does this relate and how do these things connect? Well, for the most part, you actually don't really have to worry about that, okay? HLs, you guys are going to do some things later where we make some connections between angular speed, angular frequency, and the displacement, velocity, and acceleration. But at this point, you don't need to worry about that. SLs, you guys don't actually need to worry about that at all. The one thing that you do need is with circular motion, you know that the velocity is equal to the angular frequency times the radius. Now this is for circular motion, okay? The reason why that's important is because it is going to link the speed of something to the distance that it's traveling, right? Mostly you're not going to use this a whole lot in this unit because we are mostly focusing on the wave properties, okay? The other question was, how do circles fit into waves? Well, they don't explicitly, like I say, more HL will worry about this more than SLs, and you'll see when we put everything together. I will have the SLs look in for the very first lesson on this because it is an interesting connection to make. But you should have probably noticed by now that when you're creating these waves, most of them, the transverse waves, the electromagnetic waves, that the waves are sinusoidal in shape, right? They have that curve that kind of goes up and then goes back down to the equilibrium and then back up again, right? They're generally created in such a way that is simple harmonic motion, where the farther you get away, the stronger the force is back towards the middle. It's not a parabola, it's actually a sinusoidal curve, okay? So we're going to look at, we'll skip question A because that's just a definition. You can look it up in your textbook. But we are going to look at B, where it says, consider the vibrations of 2 points on the string P and Q. All right, so it's actually talking about the displacement of point P. All right, so it's saying that P starts here. And then what does P do? If it's in a standing wave, right, it's in second harmonic mode, okay, which means that we have 2 antinodes there. We have 3 nodes, okay? P goes from here all the way down and then all the way back up. That's a complete cycle. So if I were to put that on a graph, right? So this is 4 point P, right? Point P actually starts at its maximum displacement there. And so it would be up at the top, okay? Then it's going to come down through the middle, and then it's going to go down to the bottom. Now, just like in simple harmonic motion, right, which we looked at simple harmonic motion of something going in a circle, we looked at simple harmonic motion of things on a spring or pendulum or whatever, those all had connections, right? We remember that when it was farther away, the force was greater towards the middle, so it had more acceleration. When it's in the middle, it's actually traveling the fastest, and then when it gets to the end, it's going to slow down and then head back the other direction. Okay? Now, all this is going to go into play in that as we get to the middle, the slope should be the steepest because the velocity is going to be fastest there in the middle. Okay? Then it goes down to the bottom, so it now has a negative displacement, just like this. And then it's going to go right back up, the same thing repeated, just going back to the other side. Now what we see here is a cosine graph, right? The one that I had drawn initially over here, that was a sine graph, which is the displacement of the original wave up here with respect to the distance across the string. Here, what we're looking at is specifically point P, and what is point P doing? Well, it starts up here, it goes down, and then it goes back up, right? And this is, again, relative to time. Now, how does this go into the question being asked? Well, several things that we can get, right? We've got the speed, right? We got the speed of the string, speed of the wave, which is 180 meters per second. That's given to us. Okay, now it gives us this equation, right? The equation which I wrote up here. Now, the equation, you put time in, right? And as you put time in, the particle is going to move from its top position down to the bottom position and then back up to the top position again, right? And so that's what's happening with this equation. The cosine graph will cause it to do that. So the question is, what is the period of this sinusoidal curve? Now, if you've studied trigonometric functions before, you may already be able to answer that question. If not, then, well, there's several ways that we can go about answering this question. One is to graph it. You can take this and you can graph it on your calculator, right? And you can look on your calculator and find out how much time does it take to go from one maximum to the next maximum, right? And you can do that on your calculator. Okay. Another way you could do it is you could do an insolve on your calculator. You could do an insolve of that function. Now, if you do it the first time, you could do insolve whatever the maximum is here. Do you know what the maximum is? Well, you could find it on your calculator, or recognizing that cosine goes, the normal cosine graph without any changes, the parent function of cosine of x or cosine of t looks like this. It goes from +1 down to -1 and then back to +1 again. Okay, now you should be comfortable with transformations. Even if you don't know trig functions, you should know transformations. So if this is the original cosine function, right, notice that there's some things being multiplied by t. That's going to affect the horizontal stretch of my cosine graph. But then I've also got some stuff being multiplied on the outside of the function, right? That's the 5.0 that's being multiplied by the cosine. Now what that does is that causes a vertical stretch of 5. So rather than going up to 1, the graph is now going to go up to 5 and then go down to -5 and then back up to 5 again, right? So this cosine graph, actually we know its amplitude. The amplitude is 5, okay? So given that the amplitude is 5, right, so we now know it goes from 5 down to -5 and then back to 5. If we can find out when it gets back to 5, at what time it gets back to 5, then we know how long it's taken for one cycle to occur. So you could do an insolve with this function equal to 5. Now, of course, the first time it's going to give you 0, so you need to say, well, please look for me after 0. So put a comma, 0.00001 or something, just so that it starts looking after 0, and then you should be able to solve for x, and it shouldn't be a problem. You should be able to solve for x in that way. Sorry, not x. We've got a t there. The other way to do it is to recognize that we can get the period directly from the equation. In case you've done trig functions before, if you've done trig functions, or if you know anything about transformations and what happens when you multiply by t, a normal trig graph, just normal cosine of t, has a period of 2 pi, right? It takes 2 pi to go all the way around, or 360 degrees, right? So, if we multiply that by 45 pi, then what happens, right? If we multiply by 45 pi, that is going to, remember, multiplied the inside is going to actually squish it down, okay? So we're actually going to divide by 45 pi, and then that should give us the period, which will be 2 over 45 seconds, because it does say that t is in seconds. So once you know the period being 2 over 45 seconds, then you should be able to calculate the frequency, because frequency equals 1 over period, which in this case would then be 45 over 2 hertz, or seconds to the -1, however you want to do that. All right, once you have the frequency, you should be able to put that into your same equation that we often use, v equals wavelength times frequency, and you should have the velocity and you have the frequency, and so you should be able to then calculate for the wavelength. Okay, so once you have the wavelength, you can see that the length of the string covers exactly one wavelength there, so you know the wavelength, you know the length of the string. And that's this question. I'm not going to give you the final answer. You can work through that and check it in your textbook. The big answer to many of the questions are, well, at this point, don't worry too much about the relationships between circular and trig and sine waves and things like that. But you do need to know how a trig function works. If you haven't done that yet in math class, you will soon. You will, every math class, applications and analysis both cover trigonometry, graphs, and transformations and things like that. And so at some point, yes, you will get to have a little bit more detail on that. For now, just be able to deal with the equation. You can put it, you've got your calculator, so you can put it straight into your calculator. You can do an in-solve, draw the picture, just have a general idea of what the cosine graph looks like and what the sine graph looks like, both of which we looked at here. Here with the sine graph that starts at 0, goes up and comes down and back up again, and the cosine graph which starts high, goes to the bottom, and then comes back up. All right, so hopefully that was helpful and answers a couple of questions, and if you have any more, please just let me know.